from our in-source partner today to give us a talk on 2050 net zero holistic development impact in water sectors. Michael, would you please introduce our speaker for today? And we'll get
Certainly, my pleasure. Hi, everybody. Good morning, good afternoon, Alfred. It's my distinct pleasure to introduce Alfred Hebley, who is a chemical engineer with 35 years of experience in water, wastewater, and in environmental technology. He's been involved in all phases of plant construction, from design through construction and optimization. So he comes to us with a wealth of practical knowledge, firsthand experience. I met Alfred through our in-source project, which is an international collaboration through the Belmont Forum. That the particular project focuses on food, energy, and water for urban sustainable development. And Alfred has been the leader of the water and wastewater work in that project, which includes work in Europe, in Stuttgart and Vienna, and also in New York City, in particular, looking at a potential plant to handle a build out in Gowanus, Brooklyn. That was one of the case studies of the project. But Alfred has a very wide knowledge of international wastewater treatment plant performance. He shared a lot of interesting information with me about European plants, and he will talk some about the opportunities for 100% energy self-reliance of wastewater treatment plants, possibly even positive energy. And that's really part of his integrated view that wastewater treatment plants have to be seen as part of a larger whole, that they should not just be seen as end of pipe devices, that they need to be integrated with demand response, biomethane generation from multiple sources of waste, hydrogen transformation looking ahead, so that we move towards a smart regional sector. Not just a smart city, but a smart region, and not just a city, but an industrial sector. So I look forward to his comments on this, on how we treat effluents, how we handle sludge and biogas for future fuels. And I know he will also touch, I believe, on very important current topic of micropollutants and microplastics in waste and how those can be treated. So with that introduction, Alfred, I look forward to listening to you.
Thanks a lot, Michael, for this kind introduction, and also a warm welcome from my side to everybody having time to listen to this interesting webinar series. So you have already mentioned our in-source project where I'm a member in, and where we now work together since more than 2 years, or nearly 3 years now. Got interesting results, but still not at the end. So still a lot of to do, which I want also to explain a little bit where I see where we stand and which gaps we have to solve, especially on the research part in the water sector, but in general in the food, water, energy sector, because you will see that there is a quite close linking of these sectors. So I would like to give you a frame and give you my perspective of preconditions which we should focus when we are talking about food, water, energy nexus, especially when we have to focus on the final goals and objectives we want to achieve in 2050. So what I try to explain and try to make you sensible on is that, of course, we are starting in a very different situation from the time being, but we have to decide and determine the right steps towards this 2050, which, when we will see what is required in additional infrastructure work and also in, let's say, build plants, new plants, extended plants, this will take first planning time and time for construction. So if we would develop a time frame, we will see that there is no time to lose. So these preconditions I would like to start with. Then I need to jump a little bit to the legal framework, which we should have in focus. Legal framework in the sense that we have maybe in Europe and Germany a more strict regulation work framework, because we have a dense community and the requirements on environmental impact is more sensitive in our region. But also here, looking to the final result, we have to check which requirements we have to implement or have to take care of in the future concept development. So then I would like to inform you about some basic things of energy efficiency, which Michael already pointed out, and how the connection might be to the big part of future fuel technologies. Then I would like to show you some best available technology processes and advanced and emerging techniques, which are already quite good in operation and where we have quite good experience already. But also here, when we look to the final goal, 2050, there will be a much more intensive combination of different processes, especially when we approach treated effluent reuse and tertiary and quaternary wastewater treatment. Then I have a short look on case study results, what Michael mentioned as well for the Govanes case. And then I would like to show you my starting point to determine a static simulation model where we could be able to model a district or also a regional situation with different types of energy utilization and water reuse, and give you, of course, some conclusions. So I think this is a general statement as precondition that we have to take care of that surface and groundwater is going to decrease in future due to all these climate changes, which provides, on the one hand, big rain accidents as we have in Germany and Europe the last days, which extremely flooding situation. But what is more difficult and much more to take care of is having weeks and months with less water and where we have decreasing groundwater and less flow in rivers. So reuse of purified wastewater will come to as a vital resource for protection of those drinking and surface water sources. What I think and want to point out is that best available technologies when we come to reuse of treated effluent is an important prerequisite for the efficient economic operation of advanced and emerging techniques, which means that it will not be possible to just to add some tertiary or even quaternary high technological processes when we do not have a full biological treatment and a full efficiency in the biological secondary treatment. Of course, when we are talking about food, water, energy nexus things, nutrient utilization to get nitrogen and phosphorus back, either from digestate, from the bio-waste side, which I will show you that there is, from my point of view, a close link to the wastewater treatment plant when we come to the sludge digestion and biogas side. So we have to have a look and focus to the full treatment line, which is on the water side, the secondary, tertiary, and quaternary wastewater treatment, but also on the sludge treatment, including sludge utilization as long as possible for as fertilizer, but which is, you will see in Europe and Germany, only possible until 2029. And then we will have to burn and combust all sludges and recover phosphorus later. Yeah. So it is clear that the concepts cannot be like designed in one step and everything is ready just by push the button. So it will take time, and we have to increase and extend our system step by step so that we have a working and reliable overall concept. It is clear that further R&D is required, and okay, I don't like this word master plan, but we need, and this is I think also a basic precondition which we have to consider from the beginning. We have to put on as basic precondition a district or regional or even a country-wide range for the processes, for the wastewater, for the food waste, for external biomass, and everywhere where we can integrate anaerobic processes to include the biogas side as good as possible. So now jumping to some legal framework conditions. So we have in Germany and Europe a European framework, of course, and the German Federal Water Act, where the treated effluent quality parameters are defined in detail. This is for municipal wastewater treatment and for industrial wastewater treatment. And this is, as I previously mentioned, important when we go to the design and or redesign of existing systems and make them ready for extension and application of tertiary and quaternary wastewater treatment. We have a quite new regulation since last year for the requirements for treated effluent reuse, which will help us to define the real quality needed. So this means also that we do not need always in each case up to quaternary treatment. We have to decide and look where we want to reuse in which quality. Yeah, this is an important legal requirement for sewage sludge, where I mentioned before that recovery of phosphorus from sewage sludge will, by incineration of the ashes and recovery of phosphorus, will be required in 2029. This means that in Europe, Germany, and this is already in progress now these days, that sewage sludges are not anymore allowed to be discharges for agriculture use and as fertilizers. So this is more or less now over, and the only possibility for using sludges for fertilizer is if we go to the bio-waste digestion and we go to the digestates which we have there. For those sludges, excess sludges, it will be possible for discharge to agriculture fertilizer purposes. Yeah, we have of course regulations for the fertilizer conditions, and also what is important, which was the latest novella on bio-waste, is that in Germany especially, the municipalities saw that the capacity which we gain from digestion of bio-waste by a consequent sampling and increasing the bio-waste will be an important energy factor. So this is coming more and more in the understanding of the people. So we have revised this bio-waste ordinance, but especially to really make sure that all what is related to plastic, which unfortunately is found also in the bio-waste bin, makes the further utilization and preparation for digestion difficult, as everybody can imagine. So we will really focus on these bio-waste bins, and this will go so far that from time to time, the bio-waste will be controlled, and if there is pollution with plastics or whatever, it will not be taken by the trucks and so on, and the people have to pay like penalties for taking this and utilize it somewhere else as an extra work, and this has to be paid. And we have, of course, special regulation for industrial wastewater treatment plants, which I mentioned here when we come to regional concepts, where we might have industry on place, which also might produce not a big flow of wastewater, but a big load, where also anaerobic treatment can be applied. So just one example of treated effluent values which we have to accept. This is a table where we have the most important parameters like COD, BOD, ammonia, total nitrogen, and total phosphorus. And this is the size number of population equivalents. That's 1,000 up to more than 100,000. And here you can see that big wastewater treatment plants beyond the capacity of 100,000 needs to have much lower treated effluent quality. Means also that this big installation will be able to reuse in a maximum capacity, because the organic pollution is minimized, and also the remaining nitrogen and phosphorus, which often causes problem when we go to tertiary treatment in terms of remaining biological activity, biofilm, and biofouling effects at the end of the day. But this shows also, and this is what I would like to point out here, that very small wastewater treatment systems will have higher values, but they will have higher values because the efficiency in such small systems is, everybody can understand it much better than in a big installation. This means at the same time, if we, which is a big discussion about very small decentralized installations, they will not be able, from my point of view, to have not nearly the same removal efficiency for pollution, and will not be able to have this reuse quantity required in future. So now I would like to jump to energy efficiency. To summarize it, okay, we have some 10,000 wastewater treatment plants in Germany, and as everybody knows, we have wastewater treatment plants consume a lot of energy, but also can produce some energy. And this is just a statistical evaluation where we have more or less most of the wastewater treatment plants examined, and they send their data, operation data, energy consumption to a central office of the German Water Association, where all these data are sampled. So we have a quite good understanding about special energy production and specific energy requirements. So what we see here, we have some, just to have an average figure of 14, this is kilowatt hours, always per population equivalent in year. And I will use this number often or later when we come to also static simulation modeling. So same is here for consumption. So, and the part of improving energy efficiency is of course in general, where possible, change aerobic to anaerobic sludge processes, sludge stabilization processes, which means that up to now, maybe wastewater treatment was done by anaerobic sludge digestion down to maybe 15,000 population equivalent or 20,000, which now goes to 10,000 or below. Of course, we have to upgrade the and optimize and look for machines with optimized electrical lead. But this is, I would say, for the time being, this will change in future. So I'll jump to this, time is running. This green part is just to show you the energy consumption in the aeration tank of wastewater treatment plants, which is more or less 50% or even higher, depending if we take raw water pumps for the energy consumption. But this is just to show when we come to reuse from electrolysis, where we can use the excess oxygen in future. I will come back to that. So we have a detailed overview about the consumption of wastewater treatment plants. In this will base on our case study in our of our partner in near Stuttgart, Landkreis Ludwigsburg, where we can see that depending on the size of the population equivalence and on the efficiency of how good anaerobic digestion is applied, we have plants where we have only, or we have a level below 20 kilowatt hours per population equivalent in a year, which comes to 96% of electricity self-supply. This is important to see that the production of biogas and its utilization provides a big energy part, or is a big energy storage when we come to future projects and burn it just not only in CHP units and put it into the renewable energy net. Okay, so this is just to show that in this, but the ratios are more or less the same in other cases. We have here 900,000 population equivalents, and 90% have already anaerobic digestion. So, but still some is remaining, but what you see is that 50% only produce biogas by anaerobic processes, and 40 not produce 15%, but of course the big ones all have anaerobic digestion. So this is nice, and this is in German, but this should just show and indicate that purification of biogas by biogas purification and will enable to go to produce biomethane and go directly to the natural gas net. This is one possibility in future, and another one which comes interesting is the production of green hydrogen by methane plasmolysis, where we use then the biogas and transform it to hydrogen. And what will be interesting with this type of process to get the remaining carbon, as they call it, black carbon. So it's coal, it's carbon, which can be used for tires or whatever later on. So emerging techniques. There is a big variety of processes which we have to apply, and again, and this will become much more important in future, that we need adjusted processes for wastewater treatment, either in municipal wastewater treatment or in industrial wastewater treatment, to achieve a full biological removal efficiency. And this is again required when we, as a further reliable treatment and application of tertiary and quaternary treatment. So now I jump to just some picture of, let's say, emerging systems for aeration in a aeration tank with this type of effective membrane diffuser in this shape. This is interesting when we can use anaerobic processes in industrial application, where the expanded granular sludge blanket process is applied when we have COD concentration at least of some 1,500 up to 2,000 milligrams per liter. This is the process, MBR process, which you probably also know. I just point out this process once more here because it will be one part which will be applied in future for treated effluent reuse. So we have different types of membranes, either arranged as a drum or as in flat plate membrane modules. This is how it looked like before they are implemented in membrane containers. This is a process which will be applied for advanced wastewater treatment or for elimination of micropollutants, which is a combination of ozonation, which is also well known. I have applied this concept in a large industrial plant, I think 2-3 years ago, where we used a special type of ozone reactor in combination with a biofiltration, which is an upstream filter with special media, where we had the possibility to have a further removal of persistent or non-biodegradable COD. So if you look on this slide where we have relative units, it will be possible to reduce persistent COD after full biological treatment by up to, let's say, 90%. So only some 10% are remaining. And this is very important if we would go beyond reuse, if we would go to nearly drinking water quality using reverse osmosis. With this processes upstream, it would be able to produce again drinking water, but okay, we need these processes before. This is how the ozone generation or injector for ozone look like. And this is just a filter gill, just to have a quick idea how it could look like. Okay, case study. It was interesting to have a look on this Gowanus case study, where the requirement was to find a net zero approach for a new district with some 60,000 capital. And I mean, this was just developed not having a look on the existing wastewater treatment plants, because I mean, it's clear on the practical side, we would always check whether we could integrate additional capacities in existing systems and improve and extend existing systems. On the other hand, this was a case study to show how would such a wastewater treatment look like when we build it in the district itself, and which advantages might we have. So I just made a design in the layout for a classical activated sludge system, and in concept 2 in this membrane bioreactor system. So this was just put it more or less close to scale in a certain area of this Gowanus district, and you can see, I mean, it's clear that a classical system will take a lot of space because of the secondary clarifiers, which at this high specific water consumption per capita is a big flow and leads to quite big secondary clarifier areas. Compared to that, we could have an MBR concept where we might need approximately 60% of the space of such systems, so that it could be possible in principle to integrate such types of wastewater treatment plant in cases where it is applicable, and has, so to say, more close ways to sample the wastewater and have also shorter distances for reuse of the treated wastewater. So if this would base on a system which I showed for our case study in Germany, where we be able to have some 90% self-electricity supply. And in order to achieve 100%, I calculated the energy and and assumed that we could use or could produce this additional energy by digestion of biowaste, which then ends up in some additional 20,000 residents. So if you would have a classical wastewater treatment plant, we could make the system self-electricity supplied by using additional biowaste sludge, either as co-digestion or in a separate plant. So, and just to have some figures, if we would go to the MBR system, where of course the membrane stage will consume more electrical energy, this would rise to some 700,000 capita to have enough bio-waste available for production of biogas. Just to have a ratio, but at the end of the day, it just should show that there is a big potential, of course, of integrate and make a concept with wastewater treatment, sludges, and biowaste. What is also important to point out is that the reuse potential of such a system would be that I say we could reuse 100% of the treated wastewater after membrane bioreactor system. This means that instead of requiring still, as today, when we have around 340 liters per capita and days of water consumption and would need above 20,000 cubic meters, without reuse could be reduced to some 7,000 cubic meters per day, which means this is would be close to the required water, drinking water, which we need today, having below 20,000 capita. So this means that treated wastewater reuse will provide an enormous potential, not to extend the freshwater and drinking water production in the watershed fit for New York by far. And this is, of course, an interesting aspect which has to be considered when district or citywide or regional concepts are studied. So how to achieve? So what is difficult to see for you, I just want to show it briefly. I think what we need to develop is like a static simulation model. This shows the wastewater treatment part, the digestion part, and the energy part. So what you see here is that I'm started to put the energy consumption for the main stages. I put what we get back from biogas, biomethane, steam reforming, electrolysis, where we need energy, but where we get back oxygen, which will be used for the aeration tank and will reduce the electrical consumption in the aeration tank as well. Means having such a model, including the bio-waste part, we will be able to calculate at least different electricity consumption parts, and also depending on which type of biogas utilization we think and which or should be applied. So we will be able to see on a district-wide and also regional-wide range how the energy and water capacities might be directed in the future, and which benefits advantages, disadvantages we have to achieve the net zero projections. So, yeah, static simulation is what I will prepare within the InSource project to quantify such a model and to better show the potential of the biogas utilization, not anymore just in CHP units, but for utilization to biomethane or directly to green hydrogen. When we go to regional concepts, this is also a part which developed very much in the last year, but which will develop even more in the next years, is that renewable biomass utilization with consideration of compounds in a new biological circular economy has to be considered as well. This means that we will change the biomass production just in monocultures. We will change, we have to look at the advantages using other types of energy producers, like this is a picture of a plant, it's called Sylvie, and it produces nearly the same energy by digestion. But what is important, the fibers which can be separated before digestion can be used for other purposes. And this is an important thing which has to be developed within bioeconomy strategies. Okay, so time is running. So I'll try to come to some conclusions. So again, sector coupling by biomethane production or transformation to green hydrogen, and also demand response strategies, which of course can more effectively be applied in large wastewater treatment plants, provide high potentials. Best available technology processes are required, and this we have to really have this, keep this in mind when new concepts are developed, to enable also maximal treated effluent reuse, which is in the food water energy nexus on the water part, for the water part, for the food supply, but also save the groundwater and surface water capacity is an important thing. No time to lose. Sector coupling requires, of course, research, and what I showed in this plasmolyze thing, having biogas transformed directly to hydrogen, is of course a high-tech process and has to be studied, of course, carefully. Yeah, stakeholder involvement, together with fast political decisions, would hope for implementation of complex nexus measures is of course a challenge, but seems at the same time to be also the only chance from my point of view for reaching the 2050 goals. So we have to start. What is missing on the research part is this overview, this model, which allows us for determination which processes we have to apply in the secondary wastewater treatment, in the tertiary treatment, in the quaternary treatment, to achieve the required quality of the reuse for different parts. Either if we go directly to a gray water net directly into houses, if we need reuse for irrigation, or if we go to green infrastructure where also people got in contact with reused water. There are, of course, clear requirements which we have to achieve and we have to ensure. But this shows also that the processes which we determine has to be really reliable, controllable, and available for 365 days of the year. And this is a big challenge, and therefore I think we have to take processes well known up to now. We have to develop as fast as possible new or adjusted processes, and then we will have a good chance to have the nexus for the water reuse solved, but also an efficient energy coupling over the biogas and further utilization of biogas in the energy part to renewable energies. Okay, so this is what I try to summarize, and thank you for your attention.
Thank you, Alfred, for your presentation. So far, we don't have any questions in the chat. Please, if anyone wants to make a comment, you can raise your hand. I can see it here in the screen, or write your name. Michael has a comment, I believe. You are mute, Michael.
Thank you, Neri. Thank you, Alfred, for a very wide-ranging talk. An awful lot to cover in 40 minutes, and more so very suggestive of avenues, of different avenues. And I want to applaud you for the idea that we have to think about our future state, our 2050 desired end state, and try and work backwards. But starting points matter also. So the question I want to ask you is, given your view of what the end states need to be, and given the variety of starting points from all the different plants and varieties in types of process, are there any main kind of pathways that you see for how we start on the right road? Are there certain kinds of steps, of measures that need to be considered from starting point to direct on the road, as opposed to dealing with something that handles a current problem but doesn't direct on the road out to the desired end state?
Yeah, it's a good and central question. I think we have really make and be aware that starting with this picture that a wastewater treatment plant is not anymore just an end of pipe device or whatever, and will be integrated in our water system and will save, as you could see, if we apply advanced wastewater treatment technology, a lot of fresh and drinking water capacity. I think we have to understand that existing systems have to be extended and modified so that these treatment efficiencies are really produced. And also, I think that we also should not make experiments by jumping into very small decentralized systems, not knowing what is happening in 5 years operation, but knowing that the efficiencies will be much less. So I think this is a precondition which we have to explain. But we have also to explain the benefits if we have reliable processes and a reliable process chain, starting the wastewater treatment plant, ending in the combustion of the remaining sewage sludge and recovering of phosphorus. So I think there is no other way than going this direction. But this will, of course, change the existing understanding of wastewater treatment plants and will also require preparation of investment plans, which are required. But again, if we compare, do we have water or do we not? We have to decide what we want.
In that vein, do you have any estimate of what the, I think you mentioned, but maybe you could highlight what the potential water recuperation is in terms of our use? I mean, are you talking about getting 50% of our water supply recuperated?
I say that we are getting 100% recuperated. And this is a huge amount. And this is only possible by building a new either gray water net where we have the possibility to connect the houses or whatever people to a gray water net where we replace drinking water in our houses. And this has to be started, of course, when we build new districts. It is not possible to start with this now, doing everything tomorrow. But always when the street is open, so to say, we should start to add this additional gray water pipe. And the other, just as we have an idea, 50% will be reused for green infrastructure. And in regions like Ludwigsburg or maybe also in Vienna, also for water supply for agriculture purposes. So the potential is, or my approach is 100% reuse of treated wastewater.
So, and the issue is not simply what can be recuperated and recovered for reuse at the plant, but what you're saying is that an equal issue is the distribution system to allow it to be utilized. So, I mean, it sounds to me almost like we are talking about two pipes replacing stormwater, combined stormwater systems with two pipes, and now we're talking about a third pipe for piping the recuperated water back to some distribution network.
Right, but I think this gray water additional pipe net, which I'm talking about, is the basic solution. I mean, stormwater management is of course required, and there are a lot of improvements possible, but a stormwater concept will not replace this requirement of gray water in this quality all over the year.
No, I understand that. I was not suggesting that. Yeah.
Okay. So stormwater is if you have a design for a stormwater net, which I don't know, which I do not see as a supply net in this sense, then we would need 3 nets. Yes. But I don't think that this stormwater storage is practically possible to have a supply over the year, because these are huge volumes. And
Nuri, was someone else trying to make a comment? Did I hear someone trying to?
Yes, sorry to interrupt. We have one question from Manpreet. Manpreet, do you want to ask, please?
Yeah, hello everyone. I would like to know that how the agriculture awareness and the irrigation techniques, or you can say the food resilience, can help in bringing more effectiveness in the water management, and how we can balance out the excess water used in the irrigation. And sometimes unawareness regarding the techniques can lead to wastage of fresh water also.
I mean, my where I end in my concept thinking for the time being is that I say we have to, or the municipality has to be responsible for supplying this gray water net and also this supply net direction to the area where it is needed. And so for agriculture purposes, it depends if we have like urban or vertical farming in a town, there are near distances, but if you go outside, there will be, of course, longer distances. But this has to be studied. I mean, the only chance is if we do not use groundwater for irrigation purposes, for agriculture uses, we have to build and make this additional net with reused water. I mean, the distribution itself, I have not this experience how, I mean, there are different ways to irrigate, but my approach is first to show a concept how we can bring this reuse water capacity to the place where required. And this is a huge infrastructural measure, of course.
Thank you. I have one more question here in the late messages. It says, if you can clarify a little bit more about the meaning of tertiary and quaternary treatment as used in German.
Yes. So for the time being, we have, after secondary treatment, only in some cases filtration processes, so to remove some suspended solids. What has been started for tertiary or quaternary treatment is the big part in municipal wastewater treatment for elimination of micropollutants. And for these purposes, there have been applied two different systems for the time being, which is activated carbon filtration or ozonation. What I can see in the development and for the future development is that ozonation will have some advantages because it will remove all parts of chemical compounds, which might be critical also in very small concentrations. So ozonation, maybe in combination with a filtration process, will solve these requirements for tertiary and quaternary treatment in municipal wastewater treatment. I think the oxidation process will be a solution, an important solution using ozone, and also compared to now where ozone has a disadvantage which is requiring a lot of electrical energy, is in future, from my opinion and understanding, when we will use renewable energy sources, not anymore this, let's say, disadvantages effect. So ozonation for tertiary treatment will be an important process which can be often applied for tertiary treatment in future. And I think it will be much more ozonation plants will be built compared to activated carbon for removal of micropollutants.
Thank you, Alfred. Michael, do you have any final remarks, or should we pass it to Cecilia?
Well, you know, we could go on for a long time, so I will refrain from trying to make any final remarks, because I think this has to be an ongoing dialogue. And I want to thank you for presenting to us, Alfred. And I hope this starts a dialogue with many colleagues who joined.
Of course, I hope so. Thank you as well. Thank you for attending my presentation, and stay healthy.
Thank you, Alfred. I think Krish sent a comment in the chat about the gray water infrastructure has been mandated for new construction in Sweden. So there might be additional things and innovations that coming up with the current situation with the scarcity of water and climate change. And we see all these flooding everywhere. We will continue the conversation afterwards, hopefully, and Nori is going to post the video, and we encourage everybody to engage a conversation either through direct connection with Alfred or through our LinkedIn channel. Thank you, everybody. Have a wonderful weekend. And Alfred, thank you so much for staying late on a Friday evening there.
Thank you for attending. So looking forward to get your responses and answer questions. Thank you, everybody.
Thank you.
Bye-bye.
Bye.
Bye, everybody.